Welcome back, viewers. So, in the series of the lectures in machine learning and explainable AI, we were learning about the SHAP library. So, continuing our journey towards that, there is this SHAP library that we have seen, that how it has different types of visualization tools and techniques and different plots available to understand the internal model behavior. Also, there are certain data sets inside SHAP, the inbuilt data sets that you can load and run the SHAP codes, or you can say the SHAP utilities that are there after you are training the data set on a model. Now, let's understand in detail the implementation of SHAP. So, we know that for the implementation we need to load the library of the SHAP, that is the modules and sub-module support that SHAP needs, especially for the Python programming environment. So, for this we must install those existing or the supporting modules for SHAP. So, for this we have to write this command pip install SHAP, which is a one-time command in a particular execution of a program. So, one time you have to do it. And we also discussed that if you are doing the programming on the Google Colab, then you have to write this particular installation command every time you are logging into your Google Colab. Otherwise, if you are using your local computer, that is the computer already, or the laptop has already installed this Python programming environment. So, Python becomes local to your system. In that case, you are not making use of any global server, but you are using your local processor for doing the Python programming. So, in that case, the installation command line has to be written once. So, in any case, first we install the SHAP, and then our programming starts with importing the files required for the SHAP execution. So, the second line of the code you can see on the screen, import SHAP. So, first you have installed, now you import SHAP, and you are also importing a regressor model, that is a machine learning model for doing the predictions. So, here it is XGBoost. So, always remember, for using SHAP, first we need a data set, and then we have to train a model with that data set. So, here we are training it using XGBoost. Once the model is trained, then we use SHAP to study how that particular AI model has given the predictions. How and why and what if. So, all these things are actually the post analysis. So, first we need the data set and the model to be trained. So, here we are taking a data set from inside the SHAP, that is one of the inbuilt data sets. So, here we are taking the California data set, and you can take any of the data set as your choice. And also remember that these inbuilt data sets, sometimes the nomenclature gets changed. So, if it is like California, sometimes it will be like California, California roads or something, or the California, the spelling becomes a little different. So, if it is like giving you some error, then you have to cross check whether the programmers of SHAP has done some kind of updates or changes to their existing codes. So, that way you have to change the code. Otherwise, you can always input your own data set in a CSV file if it is a numeric kind of model support requires, or if it is a image data, then you can give your image in form of different types of pictures in JPG or any other image formats. So, here we are using numeric and alphanumeric data that is in a CSV file format, that is a tabular file format. So, this is what our data set here looks like. So, you can take the existing California data set, or you can take any data set of your own. just that it should have some of the features as the column heads and some of the rows as the samples. And then we train the example model as model equal to xgboost dot xgb regressor. So this is the regressor model, and then you are using dot fit xy. So here the model gets fitted using this method fit. Now if we go ahead, then we have to explain how the model predictions are being done. So we have fit the model, and now we are using the explainer. So now explainer is a L value, you can say a variable that is holding the output of SHAP.explainer, and inside the explainer you can see the round brackets wherein this model goes input. So model is what? The model that we have just trained and fitted. And then the next line, SHAP values is equal to explainer x. So x is the training data that we have taken, and then we visualize it using the SHAP dot summary plot. So SHAP dot summary plot gives you a summarized impact of how the features are contributing to the model outcome. So for that we are using the SHAP values, the values that is used that is given by the explainer, and based on what data set, that is the x. So for the sample code, this is the implementation output that we get. So there are different features that you can see on the vertical axis, and on the horizontal axis, that is the x axis, you can see the SHAP values, and each of the dot, it corresponds to the sample. The features, how for each sample, a particular sample will have all these features, right? So how say for example the latitude, the longitude, how they are behaving for the model outcome. Now model outcome is high or low, that is what is the prediction, we are predicting the price, so it is high or low. So if it is high, then which is the set, or you can say one parameter or a set of parameters that are contributing more towards the increased target value output, and what is the, you can say the feature, that is the input features that are on the vertical axis, what were the values for these variables on the vertical axis, because of which we have got a high prediction or a low prediction. So from this graph, this become very much transparent that which feature or features are contributing to the high price or the high target value, and which are giving you low value for the target variable. So this is a summary plot. So this is not an individual plot or an instance plot, but this is a summary plot because it is taking the whole data set into consideration and giving the output. Okay, let's move ahead. Now let's see some real world case studies with the SHAP model. Now here again, as I told you just now, we have seen a summary plot. So similar to this, there are many other summary plots, and whenever the model is using these summary plots, it means that we are studying the model summary, or you can say the collective behavior. So these plots, they are there to comprehend the impact of individual model features onto global prediction. So it's a collective behavior, it's showcasing the collective behavior of the model. So for this, different summary plots are available that we will see shortly, and similar to that we have some model instance plots. So if we want to see that, no, we are now focused on each and every sample, okay, not the whole data set, but I want to look at one sample, one by one. I want to see the samples and how the prediction for that sample has occurred. So this is the individual sample behavior. So earlier the summary plots will show you the collective behavior, and the instance plots will give you the individual sample behavior. Okay. So now if we move ahead to what are the different model summary SHAP plots that are there. Let's see. So, the first one, the feature importance SHAP plot. Feature importance, as the name goes, it shows that how important a feature is when it comes to the model prediction. Now, every time I am saying it as a model prediction, but remember that model prediction is just abstract term. It could be anything, any machine learning task. It could be model prediction, model recommendation, model association, anything. Okay. So, as your model is built for whatever purpose, for recommendation purpose or association purpose, or classification purpose, clustering purpose, or simple time series prediction purpose. So, for that the feature importance will be given. So, if I am doing just a model prediction, as I am using prediction as a very abstract term. So, for that kind of model and for the prediction provided by such models, how the input features are important. So, this input features is importance of these features, it is showcased using the feature importance plot. And it is obviously highlighting the global significance, that is why it is one of the summary plot. And for example, if we if we take up an example like the soil pH prediction, okay. So, based on some of the soil properties like the presence of clay, sand, silt and many other input parameters, we want to predict what is the pH level of the soil. So, for this we have a soil properties data set, and there are some major elements and micro elements, some soil properties as the input features. So, we have taken this particular soil data set. So, for the soil data set, if we are drawing the feature plot, then it will look something like this. So, the plot that is having maximum importance, it will be on the top. So, the feature importance plot by default it gives the sorted output, and in the descending order, that is the element or the input feature that is having most importance with respect to the model outcome will be given on the top. Okay. So, this is your feature importance SHAP plot for the soil pH data set. Okay. Now, moving ahead, say we have another plot like the feature plot, we have summary SHAP plot. Now, summary SHAP plot is given in form of a bee swarm summary plot. So, what the plot that we have just seen for the feature importance was a horizontal bar plot. So, now we will see the summary plot, just another way of summarizing the model behavior using a bee swarm summary plot. So, here we use the different features, that all the input features are plotted along the vertical axis and the SHAP values are on the horizontal axis, and each point in the SHAP summary plot will denote an instance for a specific feature. So, that way you can view this as a collection of this many instances that a data set is having. So, if we look into this plot, it is something like this. We have just seen a very similar kind of plot in one of our earlier examples. So, now, this is with respect to our soil data set, and again you can see that the output that is here, the output is the pH level of the soil. So, it can be high or it can be low, and on the vertical axis there are certain features. So, looking at each feature you can see that which are the features that are contributing to the high value of the soil pH. So, likewise the model outcome becomes very transparent and easily readable by the end user. So, the end user may be a soil expert or he may not be. So, it does not require the domain specific nature. Anyone looking at the explanations provided by SHAP can understand what is the why the prediction has came and which are the contributing features that is that has given this particular outcome, or that has more given the higher values and maybe in some cases the lower values. So in this pH summary plot, we can see that Fe and Mn are the micro elements that have higher importance for maximum samples in the inverse aspect. Okay, so not in the like towards the higher, but in the inverse aspects, Fe and Mn are having importance. Then there is dependence Sharp plot. So this is the third in the category where you can see that it's a scatter diagram, and here the model that predictions that we can see that is being described by this plot is specific to a particular feature. Okay, so it can give you the outcome of one feature with respect to another feature. Okay, so a point in the scatter plot, it represents the model outcome, and the horizontal axis, it is giving you the feature centric value. And here the vertical axis, it is showing the Sharp value, that is showcasing that how the feature is influencing the model predictions and all. Next one is the dependence. There are different ways in which dependence plots can be seen. There is you can also see that for a particular feature, which is the most or you can say the largest interaction, giving you the largest interaction. So in this case of the dependence plot, the figure is showing the dependence Sharp of Mn for pH prediction, especially with respect to one of its counterpart that is having largest interaction. So whichever like feature is having the largest interaction with the primary feature. So you can say that this is a interaction between the primary and the secondary feature. You can take any one feature that acts as a primary, and with respect to that primary feature, which is the secondary, that is the second largest feature that is having the largest interaction when it comes with the primary feature. So that is what the dependency is. Primary feature is dependent on the another feature, and thus having the largest interaction effect. We also have a decision plot where these are the lines that you can see on the screen. So each line on the plot, again, it denotes the contribution of one feature. So if we had just one line on the plot, then it means that we are seeing one feature, or you can say one sample study. And since we have a collection of lines here, so decision Sharp plot in this case, in this plot that you can see on the screen, is behaving as a summary plot. If there has been just one line, then it will behave as a individual or a sample specific plot. So decision plot is one that can behave as a summary as well as the individual specific plot. So in the decision plot, you can see that in this case, as it is giving the summarized view, so it's providing you a comprehensive view rather for the prediction dynamics, how the prediction is evolving from an expected point or a value from the x-axis relative to individual sample values that are evolving as the model is getting trained. We also have heat map Sharp plot. Again, this is also a summary plot, and it is basically for another data set, not the soil data set. So here we have different attributes here, the age and from where a person is belonging to, and different factors that are taken as the input feature in the vertical bar, and the prediction is given that whether the income is high or low. So again, you can see that what are the features that is contributing towards high income, and what is the nature of the distribution of the data or of the target variable, that is shown in the like vertical bars on the vertical axis, secondary axis, and also as the line bar on the top. And you can see there is a line also, a constant line showing the average. So many things are being communicated by a single heat map SHAP plot. Now let's see the model instance plots. One important plot that helps you to study each and every sample is the waterfall SHAP plot. So this plot, it provides you a very detailed understanding of how a prediction is performed by studying it from the base value, or you can say the expected value of the model, and how the gradually the waterfall model is giving the outcome, a particular prediction. So like it starts from an expected value based on the whole of the model, the average behavior or estimated behavior, and then for each of the sample specific the feature specific values for a particular sample, this the final prediction for that particular sample, how it gets evolved to the value that you can see on the top right corner. So it is the journey of the value, the sample specific prediction value, from the expected, the model, average model behavior, starting from the average model, you can say the prediction, to the sample specific prediction. And finally, each of the feature is having some contribute to the outcome of the model, the prediction of the model. So this is your waterfall model. Now in waterfall model, as you can see, there are different colors also to distinguish between the positive and the negative. So if some feature is having a negative aspect, then it will show it on the negative bar, else it will be on the positive. So here you can also make out that what are the features which are the the prevalent features that are contributing to the negative or the positive contributions of the model. Next is force SHAP plot. Now force SHAP plot is completely a horizontal plot, and here the direction and magnitude is important. So the values, the feature centric values that are giving a negative impact, the direction will be shown in the negative way, and if it is a positive, then the direction will be towards the positive axis, and the magnitude is also shown. So the one that is having more impact will take a larger size, and along with, you can see the values are also given, and finally the features, they impact, provide the impact, the numerical impact rather, towards the model prediction. So the features in red are here, in this case they are showing the increasing of the values or the chances of a positive target value, and the blue features, they are lowering the chance. So this is a data set that is particularly on the reviews, to study the sentiment of the reviews, positive or negative. So the red features, that they are showing the increasing chances for a positive review, and blue features are just the vice versa case, showing the chances of getting less chances of getting the positive reviews. Then we have decision plot, which just a few moments back we were discussing that decision plots are, we have seen the decision plots primarily as in form of summarized summary behavior of the models. Here you can see that how if I am taking out just one line out of the plot, that is each of this line, they signify the individual samples in the data set, right. So here if we have a number of lines, so it means that if we take up just one line, we are studying one sample or one individual case from the data set. And not just the local interpretations that we can draw out from decision plots, but also we can do different other things like the outlier analysis. So, if we want to see that which are the outlying points, we can find it out and highlight it through dotted lines, as you can see on the second plot, and then we can altogether study the dotted plots using these particular commands. So, first we can find out which line was misclassified and how you are doing it, just to see that the test set and the prediction, if it does not match, it means that it is a misclassification, it is a wrong classification, and then we can highlight it in a dotted line, and then it becomes very easier for the end user to see how and why the model is being misclassified. So, is there a model retraining required or not? So, one can decide using this decision instance SHAP plot. So, viewers, we had a very detailed you can say study of the SHAP plots, different types of SHAP plots, be it summary plot, be it instance plots. So, we have seen many SHAP plots along with how the SHAP library is loaded, it's installed and imported. So, it has been a very not just the tools and techniques, but also we had an overview on the code part of the SHAP, from implementation to execution. So, I hope you have enjoyed this lecture. We will have many more on this particular topic in the upcoming sessions. So, for then, thank you.